In this example problem, we're going to be looking at a poll, and based upon the results of this poll, we are going to construct a confidence interval about what it expects to say about the greater population. For example, in this poll, we're looking at a group of U.S. adults, 1,040 to be exact. And while they may feel a certain way, there is no guarantee that the way that they feel is truly representative of the entirety of the U.S. population. So what we're going to do is apply the central limit theorem to go through and make a statement about, based upon the results of our poll, what we think the U.S. population feels about the same subject. And we can't say it's definitively the same, so the best way to go about doing this is to construct a confidence interval. So our situation is that we did a poll of U.S. adults asking whether or not they would trust robots to perform surgery on them. And from the results of our poll, 743 out of 1,040 respondents said they would feel comfortable. Yes, I would feel comfortable having a robot perform surgery, at least minor surgery. So what is the sample proportion, the p hat, if you will? It is your x divided by your n. 743 out of 1,040 respondents said yes. So if we take 743 and divide it by 1,040, we essentially get the percentage of respondents that said I would be comfortable having a robot perform surgery. Question tells us to round to 2 decimal places, so I'm going to go back into this cell and I'm going to set it inside the round function, so equals round, open a parenthesis. That formula is what's going to give me the number that I want, and I want to round to 2 decimal places, so equals round, in parentheses, your formula, D3 divided by D4, comma, 2 for 2 decimal places, and the parentheses. And we get 0.71. So 71% of our respondents, roughly, said that they would be comfortable having a robot perform minor surgery. We don't know what the population percentage is. This is something that's kind of new. We can't go to some reference thing and say, well, 80% of the US feels this way. We don't know what it is. So we have to make an assumption about the population's proportion, the percent of people in the whole entirety of the US population that would feel this way. And to do that, we're going to use the central limit theorem. And there's 3 rules that you need to meet to have this apply. And by apply, I mean you can assume that the overall population is similar to your sample population. The first is that when your experiment or your survey or whatever was conducted, it was random. So you didn't bias the survey by only asking people that you expected to respond in one way. And also that it was independent, that this group of people that you're surveying right now didn't have influence on a previous survey of the same thing or a very similar survey. And in this case, in the top, it says, assume that the sample was conducted at random and is independent of other similar polls, which means this is a big fat yes. Essentially, what you have is a proper accepted way to conduct a survey of this order. And then this other number that's very important for CLT is 10. The first one is you need to have a large enough sample, and you need to have a proportion within that sample where you would expect for any survey that you give that at least 10 respondents are going to respond for each of the variable outcomes that they could have. In this case, is our survey big enough, and with the proportion that we're given, could we expect if we did another survey to get at least 10 yes responses and at least 10 no responses? And there's different schools of thought about going about this. I could just bring on the 743 for the yes if I wanted to. The way that I like to do it is I like to take the sample proportion and multiply it by the sample size. And since we rounded here, we're going to get a slightly different number than 743. So if we survey another 1,040 people, and we expect 71% of them to respond yes, just like it did in that survey, we'd expect 738 yeses. Well, we'd be surveying another 1,040 people. There's only 2 options they have, yes or no. So if 738 say yes, the remainder of that 1,040 have to say no. So you can find your expected no's in this case by just taking 1,040 and subtracting out 738. So if we did this again and then the same proportion held in our next sample, we would expect roughly 738 yeses and 302 no's. Well, both of those numbers are far bigger than 10. So the large sample condition for CLT applies. So we got two of the three things knocked out. The third one is the big population condition applies. And in this, you want to make sure that when you're doing the survey, you're not capturing anything definitive, that you are declaring that this is the population thing, that you are, in fact, taking a survey, a sample, that is a portion of a much bigger population. And the 10 number still applies here. For this to meet, the population has to be at least 10 times the size of your sample. Well, what did we sample? US adults, and we sampled 1,040. 10 times that would be 10,400. There are way more than 10,400 adults in the US. So down here for our big population, does it apply? Absolutely. Yes, it does. So just as a refresher for the three conditions where CLT is going to apply, you need to have a, for lack of a better term, fair way of conducting this, that you did do it randomly. You did do it according to proper statistical procedures. You're keeping this independent of all the results that you had. The second one is the large sample condition. You need to have a sample size that is big enough based upon the proportion that you have where you can expect at least 10 people to respond to all of the different variables that you're allowing them to respond with. And the third one is that your population that you're taking a sample of, the entirety of that population has to be at least 10 times the size of your sample. We met all three of those. Yes, yes, yes. Which means CLT applies. And by CLT applying, what we can do now is we can go through, follow the same procedure I did in the screen time example earlier, and we can operate under the assumption that our population proportion, this P, is going to be very similar to our sample proportion of P hat. So since CLT applies, we can make the assumption that the population proportion is also 0.71. And now I can use my standard error formula down here to figure out what my standard error is going to be for further calculations. So this is equal to the square root, open a pair of parentheses, of P, the population proportion. And since we passed CLT, we're going to assume that's the same as our sample proportion of 0.71 times, in parentheses, there we go, 1 minus that 0.71. Close those two parentheses, and that is the numerator inside of our, the fraction inside of our square root over here. P times 1 minus P. Now I just need to divide by our n, which was the size of our sample, which going up to the top was 1,040. And coming down, I can close this last parenthesis and enter, and I get 0.014. So standard error is standard deviation for a proportion. Every sample we take of similar size, we can expect the sample proportion, which we're going to assume is the same as the population proportion, to be somewhere within 1.4% of the 71% that we got above. And with that, I can calculate my margin of error. And my margin of error is found as our z-score for the confidence level that we are using times the standard error here that we just calculated in requirement 4. The most common confidence level that you have for intervals is 95%. In the PowerPoint for Chapter 7, there is a slide in there that has the entire list of all of the different z-scores which coincide with a particular confidence level. So it's known that a z-score for 95% confidence is 1.96 because you expect 95% of the data to be below 1.96 standard deviations or standard errors in our case above mean. So I can just fill in this formula now because I know z and I know our standard error. So this is going to be equal to 1.960 times our standard error of 0.014, and it comes out to 0.028. And now I just got to go through and determine the upper and lower bounds of my confidence interval. And the formulas for them are listed on the side over here. For your lower bound, you take your sample proportion, subtract from it your margin of error. And for your upper bound, you take the sample proportion and add to it your margin of error. So our lower bound, our sample proportion thus far has been 0.71. We're going to subtract from that the margin of error that we just calculated is 0.028. It comes out to 68.2%, or if I want to put it into decimal form, there we go, 0.682. The upper bound is going to be equal to that sample proportion plus our margin of error. And our margin of error is still, as soon as I scroll there, 0.028. And that comes out to 73.8%, or just like before, if I put it into a decimal, 0.738. So what does this mean? We're saying that based upon this sample that we have right here, that we took, in which 71% of respondents said that they would be comfortable having a robot perform minor surgery on them, based upon the sample, if we had enough information for the entire population, we would expect the percentage of the entirety of the US population that would be comfortable having robots perform minor surgery on them to be somewhere between 68.2 and 73.8%. And then you're going to use this information to make some type of claim. Politicians do it all the time in elections. You know, I'm a big sports guy, sports analyst all the time, make some sort of claim about how many wins somebody's going to add to the team based upon their contract. Like, you make claims based upon the data that you have. And we are comfortable making this claim with 95% certainty that the true population mean is going to exist somewhere within these two numbers. So our claim here, if we wanted to make a news report and say in it that we are 95% confident that 2/3 or at least 2/3 of US adults would feel comfortable having a robot perform surgery on them, do we have the data to back this up? And the answer to that is yes. And the reason why is because every number in our confidence interval, from the low end to the high end, exceeds the number that we have, exceeds our condition. If the lower end of this was, say, 0.662, well, then we couldn't say that because we would have numbers within our interval that are below the number that we're looking for. But it isn't 662, it's 682. So that's above 667. At least we can say definitively, at least 2/3 of US adults, based upon this survey that we had, will feel comfortable having a robot perform surgery on them.